Hello everyone, welcome to Lesson 5, Integration Using Substitution. Now you'll notice that as they often do, this lesson starts off with a box full of information written in dense mathematical notation. I'm going to skip that entirely. You can absolutely take a look through it. It would be wonderful if when we're done you can look at that and understand what's going on with it. But honestly, it kind of doesn't matter because what matters is that you know how to use the tool that I'm going to be teaching you. So I'm going to skip it and just go to an example. I think that will make more sense. So substitution is something we can use when we come across a problem like this. This particular integral is definitely more challenging than what we've done before, and it's really hard to say what we can do here because remember, we cannot just apply integration to these two parts separately. We're just not allowed to do that. Just like we can't apply the derivative to the numerator and denominator separately. We have to use quotient rule for derivatives of quotients. And in integrals, though, well, there's no easy rule here. So we're going to have to figure out a different strategy. So what I want to do is I want to try and simplify this function to something that's a little less complex using substitution, as we have often done in the past for derivatives. So the hardest part I find with substitution, the hardest part is choosing what your substitution is going to be. A really common thing is that people will say, oh, let's set u equal to, x squared over the square root of 1 minus x cubed. Except that's not really all that helpful because then you'll still have to end up taking the antiderivative of x squared over 1 minus x cubed. So that's not it. And then people will often pick, well, let's set u to the square root of 1 minus x cubed. Let's try that. But again, this one's still more challenging than we know how to deal with. So we want to make sure we pick something we know how to take the antiderivative of. So I'm actually going to pick, and you'll kind of see why later. The more we do this, the more you'll understand why I pick the things I pick. But I'm going to choose 1 minus x cubed because that's that interior function that's kind of in the way. Now, I want to be taking this integral using u with respect to u, right? I'm no longer using x as my variable, I'm using u, meaning I can't use dx, I need to use du. So what I'm going to do is I'm going to try and figure out what du dx is. So du dx is the derivative of my u. So the derivative of 1 minus x cubed, and that is negative 3x squared, is my du dx. Okay. Bear with me, this is where it gets interesting. So I'm going to actually rearrange this in terms of dx. So if du dx is equal to negative 3x squared, then I can rearrange this. Dx is equal to du over negative 3x squared. And see, now what I've done is I've taken that dx and I have found an alternative expression that represents the same thing. I've substituted not only my 1 minus x cubed, but also my dx. Watch what happens. So my original function was x squared over the square root of 1 minus x cubed dx, right? But I've made some substitutions. I have determined that I want to replace 1 minus x cubed with u, and I want to replace dx with du over negative 3x squared. So in other words, I want to replace that, and I want to replace that. Okay, check it out. This becomes the integral of x squared over the square root of u, and then I replace my dx with du negative 3x squared. Okay, hopefully you're seeing the awesomeness that just happened, and the reason why my u was such a great choice. Check it out. These x squareds cancel, and I've just gotten rid of that extra variable that was going to cause me a bunch of trouble. Because remember, I'm not going to be able to do this with two different variables. I need to keep it to one. So by doing that substitution, I got rid of that additional variable. Now I can rewrite this whole integral as, well, I can rewrite that 1 over square root of u, I can rewrite that as u to the negative 1/2, and I can put a negative 1/3 out front, and it's all du. Awesome. Now this is something I know how to work with, so I can take the integral of that. We know how to do that. So we're just taking the indefinite integral right now. I'm not really worrying about definite integrals at the moment. So we take the indefinite integral. That's going to be negative 1/3. Always just leave that coefficient out front. And then we're going to have our u, we're going to add 1 to our exponent, so it's going to become positive 1/2, and then we're of course going to divide by that 1/2, just like we always do. And don't forget, because it's an indefinite integral, we need to go back to adding our plus c. And then I just simplify. This becomes negative 1/3, negative 2/3, because I'm just going to combine those two together. Square root of u plus c. And finally, I finish off by substituting my u back in. And if you recall, u was 1 minus x cubed, so I just replace that again. Bada bing, bada boom. So figuring out what to set as your u or your substitution, that's the trickiest bit. And there are basically two factors you're looking for. You need something you can take the derivative of relatively easily, and something you can take the antiderivative of when you do your substitution. But you also want something that when you isolate for dx, it helps you simplify the expression. So it's something that takes a lot of practice, and the more you do it, the better you get at seeing it. But let's take another example. Determine the integral, the antiderivative, of 2 plus sine x all to the power of 10 times cos x dx. So again, we have to pick our u. So here's my interior function. That seems to be a good starting place, especially because I know that the derivative of sine x is cos x. So when I take my derivative of my u to find my du dx, pretty promising I'll get something that will help me simplify. So I'm going to set u to be 2 plus sine x. That means that du dx is going to be, well, the derivative of 2 is 0, so that goes away. Derivative of sine x is cos x. So you see how the more you do this, the more you get good at spotting, oh, hey, this is going to work out nice. Which means that dx is equal to du over cosine x. Okay, now I rewrite my integral. So now I have, instead of 2 plus sine x, I have u to the power of 10. And instead of dx, oh, sorry, I forgot my cosine x. There we go, cosine x. And instead of dx, I have du over cosine of x, which works out spectacularly. And so I'm left with the integral of u to the power of 10 du. All right, now I know how to take my antiderivative. I'm going to add 1, divide by that 11, that new exponent, and of course add c because this is an indefinite integral. Now I go back and do my substitution. This is 1 over 11. This becomes 2 plus sine of x to the power of 11 plus c. And that's it. Or if you prefer, that 1 over 11, I don't know, something about it's making me feel weird. I don't know why. It just looks like not numbers. So for my own sanity, I'm going to just do this. It doesn't matter. I just didn't like it. And that's it. That's the answer. The other previous step is also perfectly fine. All right. You know what's next? Try. So again, give these a shot on your own. See if you can figure out what the u and then what dx should be. Look for something that's going to help you simplify this. And then you can go and check and see if you got the same thing as me. So I'm going to let u equal 1 minus x squared in this case. That's my nice interior function there. Derivative of that is going to have just a singular x with the power of 1 on it. So du dx is equal to negative 2x, which gives me that dx is equal to du over negative 2x. All right, got my integral. So this is now equal to x times u to the power of 10, and my dx gets replaced with du over negative 2x. All right, x cancels with this x. That's delightful. What I'm left with is negative 1/2 u to the power of 10. Should probably still have an integral sign there. Du. This we know how to do. This becomes negative 1/2 u to the power of 11 over 11. Apparently I really like powers of 11 today. Don't judge me. It's just I like 11. Actually, that's true. 11 is, in fact, my favorite number. True story. I'm quite fond of it. All right, finish off. This one doesn't bother me. This one is nice, so I'm not going to change its format. And I'm not going to explain why the other one bothered me and this one doesn't. It's just, we all have our quirks, and I have lots of them. All right, there we go. B. Okay, so yet again, we need to decide what everything's going to be. So I'm going to let u equal x cubed plus 2, which means du dx is equal to 3x squared. That's important. Which means dx is equal to du over 3x squared. So my new integral is going to be x squared, square root of u, du over 3x squared. The x squareds delightfully cancel. We've got the integral of u to the 1/2 du over 3. I forgot the over 3. Don't forget if something gets left behind, like I just did. Don't forget about that. All right. So what this gives me, this is 1/3 u to the 3/2 divided by 3/2 plus c, which, if you simplify it, gives you 1/3 times 2/3 times u to the 3/2 plus c. Do my substitution. This is 2 over 9, x cubed plus 2 to the power of 3/2 plus c. Another one done. One more of this try set. So, in this case, we're going to let u equal to 1 plus 2x to the power of 4. Then that gives us that du dx is equal to 8x cubed, which gives us dx is equal to du over 8x cubed. All right, neat. So I can rewrite this as the integral of x cubed u to the power of 4 du over 8x cubed These cancel. This becomes the integral of 1 over 8 u to the power of 4 du, which is 1 over, I'm taking the integral, 1 over 8 u to the power of 5 over 5 plus c. And when we substitute back in, that becomes 1 over 40, 1 plus 2x to the power of 4 to the power of 5 plus c. Easy peasy, beautiful cover girl. That ended differently than I started, but I'm not mad at it. Okay, let's try another kind of problem. Similar idea, nothing's really changed here. We're just going to branch out a little bit. So let's look at some exponential logarithmic functions. So determine the definite integral. This one we've got a definite integral, so let's practice that as well, of ln of x over x, e to e squared. So we have to do the same thing as before. We have to choose a u and a du. I'm going to choose u to be natural log of x. The reason for that is because the derivative, du dx, would then be 1 over x, which means that dx is equal to, if you're keeping score, x du, which is going to allow me to cancel out those x's. So now, here's what I'm going to do for now. I'm just going to ignore the definite integral, and I'm just going to work out the indefinite integral for now. There are some notations I can use in the meantime to keep it as the definite integral, but I don't want to. So I'm just going to deal with the indefinite integral first, and then we can deal with the definite integral after. So here's my indefinite integral. That one's just going to be the indefinite integral of ln x 1 over x. I'm just rewriting it like this. And that's going to be equal to the indefinite integral of u times 1 over x du. Just doing all my substitutions there, replacing my ln x with a u and replacing my dx with x du. Okay, when I take after I've canceled these, delightfully, that gives me the integral of u, that's still red. The integral of u, no, I don't regret it. The integral of u du. Oh, what could be easier? What could be easier than that? That is a beautifully simple integral. I love it. So that's add 1 to the exponent there, becomes u squared, divide by that new exponent too. It's just our basic power rule for integrals. And then I do my substitution, and I get the natural log of x squared all over 2 plus c. Okay. So what this means is that I can take my definite integral as such. So this is from e to e squared of ln x over x dx. That's going to be equal to the natural log of x squared over 2. That's our indefinite integral, and we can ignore the c because now we're taking the definite integral, I should say, from e to e squared. So what we get when we do that is that's going to be the natural log of e squared, all squared, over 2, minus the natural log of e all squared, all over 2. Now, the nice thing is, we can actually rewrite this using log rules as 2 natural log of e all squared over 2 minus natural log of e all squared over 2. I ran out of room. I wrote really big. I wrote a lot bigger than I did in my notes. I had lots of room in my notes. All right, almost done. So this is going to be equal to, well, the natural log of e, that's an easy one. Natural log of e is 1, right? Log base e of e, it's going to be 1. So this is going to be 2 times 1 all to the power of 2 all over 2 minus, again, natural log of e is 1. It's going to be 1 squared all over 2. And that's just, well, that's just 4 over 2 minus 1/2, which is 3/2. And there's our answer. Not so bad. Okay, we're almost done. Last one, problem 5. This one's back to a nice indefinite integral. A little more complex, but they've given us which one to use for our substitution. They helped us out a little bit here. So we're going to let u equal to x. I'm just going to rewrite it as x to the 1/2. This means our du dx is going to be equal to 1/2 x to the negative 1/2, which means that dx is going to be equal to 2x to the 1/2, just by rearranging. So when I move that x to the negative 1/2 into the denominator, it's going to just change the exponent there. So that's what we've got. Let's go into our integral. Make sure you are checking that you're able to get all of these things. I skip a lot of the algebra because I do expect that you guys can do the basic algebra parts of it, but do make sure that you can. That's important. So I'm just going to rewrite this as e to the power of x to the power of 1/2, okay, times x to the negative 1/2. And if you do have any trouble, if you're not sure where some of my numbers are coming from or how I'm doing my rearranging or my algebra, just ask. I don't mind explaining it. I just don't want to make these videos too long, you know? I understand how hard it is to keep your attention on a 20-minute video as is. So, I know not all of you watch the whole thing, which is totally fair. But that's exactly why I don't expect you to watch the whole thing. It's a lot. So try and pare it down. So we're going to replace that square root of x. The reason why root x was such a good choice here is that's both my denominator and my exponent. So that actually helps me in 2 places. So what I get then is this becomes e to the power of u times, and my x to the negative 1/2, right, times 2x to the positive 1/2 du. Now remember, these two, since this is -1/2, that means it's in the denominator, so these two actually cancel. Not the 2 though, just these things. Again, you can rewrite it as 1 over x to the 1/2 if that helps. In fact, I will do just that, just to be extra clear. So these cancel out really nicely. So what I'm left with is e to the power of u, I forgot the 2, 2 e to the power of u, I always do that. Don't do what I do. Oh well, do what I do when I do things right. Don't do what I do when I do things wrong. Anyway, taking the indefinite integral of that, I promise that makes sense. Remember, we can ignore the coefficient. That doesn't make a difference. So remember, the integral of e to the power of u is just e to the power of u, just as the derivative of e to the power of u with respect to u would be e to the power of u. So this is just 2 e to the power of u plus c. Then we do our substitution, replace our u with square root of x, and we are done. Ta-da! And remember, all of these, you can check your work by just taking the derivative. Go ahead and just take the derivative, and if you get back to this original thing, then you did it right. All right, and that's it. Thanks for sticking with me. This is probably one of the tougher, cumulative things. It takes pretty much everything we have done all year into one big problem. It's got all the different derivative rules are involved in here in some ways. We've got integrals in here. We've got, algebra with substitution, lots of good stuff. So do your homework, get some practice. Let me know if you have any questions. See you later.